As you can see, key factors and methodology for boiler room assessments is yet another one of those topics that our audience has been asking for. Is, you know, companies are continually striving to get a handle on their operational costs, especially relating to the fuel spend. But, you know, other operational factors as well, which ultimately impact the bottom line. I'm talking about things like production uptime, product waste, environmental impacts, reputation, and of course safety within the facility. These are all things which are considered when conducting a thorough and complete facility assessment. But we're going to be primarily focusing on the boiler room portion of an assessment today because of the relatively small amount of time that we have. But let me quickly add that what we will be covering today represents a major portion of what would be covered in a complete facility audit or an assessment. So today, this is what we're going to be covering, the boiler room assessment cornerstones. The areas impacting these cornerstones, and I'll explain all of this. And then, of course, we're going to show you the logic or the assessment methodology. How does an assessor go through a plant audit or an assessment effectively? And then typical discoveries that we find and or other assessors from other companies might find. And then I'm going to talk a bit about the final report that one would get. And then, of course, we'll conclude as we normally do with a summary, and then, of course, the Q&A that Susan had mentioned. Now, as stated, we're going to start today's discussion by reviewing the cornerstones used for any boiler room assessment. And they consist of the following, as you can see on the screen: efficiency, sustainability, reliability, and safety. And any facility which has a good handle on these areas will be optimized, and they'll be performing at their highest level. And to get there, it requires a specific methodology and expertise, oftentimes not found in the facility itself, but rather the organization needs to seek help from experts who just specialize in this discipline. And once the outside resource is chosen and engaged, now I'm assuming here that no inside resource is available, the next step is to engage the key personnel within the organization who will have a high stake in the energy conversion process. Now, these people need to understand the objectives and then be committed to making the necessary changes to render the positive results that will be sought. For instance, maybe it's only efficiency and safety which need improvement. So these are the areas for the expert to focus on and deliver recommendations with justifications. Or maybe we need to focus on all the cornerstones. As we see, we have weaknesses throughout the organization, throughout the facility, and there's a good deal of synergism between the areas anyway. So let's begin by looking at the four cornerstones and then discuss what areas fall under them, which will impact the difference, while at the same time showing you the logical progression and methodology normally imposed or employed in these assessments. And we'll start with efficiency. Now, those of you who have been attending previous webinars have certainly seen this slide a lot, but I wanted to show it again because it just so well depicts the significant operational spend that's associated with the fuel and its cost. And when we talk about improving efficiency, well, that's primarily what we're talking about: saving fuel, saving large operational dollars. And as you can see in this chart, saving energy by improving efficiency goes beyond the border, which, as you can see at the bottom of the chart with the orange arrow, represents the biggest opportunity as a single source. But an experienced professional knows there are many other areas which can be attacked in the boiler room and just beyond in order to save massive amounts of energy dollars, and we'll be touching on these today. So let's go back to our initial discussion with the energy conversion team. After the preliminary establishment of cornerstone focus, and knowing we at least want to concentrate on efficiency improvement, it's time to begin drilling down into the specifics. Things like, give me an example of equipment descriptions, including the age. In other words, I want to know exactly what that is. What about maintenance and service records? Do you have any P&ID drawings? What about your standard operating procedures? We want to take a look at that. Operating conditions, including the load recordings. Do we have some steam charts? Do we have something that's going to tell us what this load is, how it swings, how it varies? What about emission requirements? Are we in a very stringent area like California or maybe some other local place where we're trying to control these emissions, be it NOx, be it SOx, be it particulate? What about the steam use? How am I using the steam? Is it strictly process? Is it process heating? Is it process heating and humidification? What is it? And then what about the staff? What about the number of people that are involved with this energy, with this conversion? And what about their experience level? And fuels, what are we burning? Number 2 oil or gas, propane, what is it? And what's the cost of steam? Well, normally we find the cost of steam per 1,000 pounds is about $7, but this varies, it can go higher. But then is this a loaded cost or is this an unloaded cost? Well, what does that mean? Well, it means exactly what's on the screen now. And I can't begin to tell you how many times when people are assessing steam costs in a boiler operation, it's the unloaded costs on the left which are applied for justification, forgetting about the other collateral costs associated with the production of 1 pound of steam. So the true professional will know this. And when asked to compile the true costs, will apply the loaded costs as shown, as this is the true reflection of steam production, the steam production spend. So it's the cost, the boiler efficiency, the condensate, but then it's the labor, the maintenance, the chemicals, the water costs, the waste costs. These are all collateral spends. So now we've drilled down, and we know the type of boiler or boilers that we have, what they're burning, their capacity, and what at least the approximate cost of the steam is. The next step in the methodology is to determine the boiler's efficiency. And to do this, one needs to understand there are various terms applied to efficiency, and you need to understand the differences. For instance, sometimes combustion efficiency is used as a reflection of boiler efficiency, when actually this is really the ability of the burner to combust the fuel with the least amount of excess air as possible, without exceeding or compromising acceptable levels of carbon monoxide and, of course, safety. And then we have thermal efficiency. Now, this is the overall boiler efficiency before subtracting the radiation and convection losses. In other words, thermal efficiency includes radiation and convection losses. Now, these are given up to the boiler room, which is already 120 degrees, so they're not going out to the process. So what we are looking for is fuel to steam efficiency. This is the true reflection of how the boiler is performing, as this is net of radiation and convection losses. It's a true indicator of the useful energy that's going out into the system. Now, determining the fuel to steam efficiency begins with a close look at the burner, its physical condition, and the features, including its turn-down capability, because we need to establish the actual efficiency during various firing rates. And this begins with the use of a good stacked gas analyzer, which registers what you see on the screen now: temperature, excess air, efficiency, carbon monoxide, and possibly NOx, though this does not affect efficiency per se. But many analyzers include this feature because of the emission laws enforced today in various locations throughout the country, as I mentioned. Now, I said begins with this analysis because it will get you close to the actual efficiency. But to really determine the actual efficiency of this boiler, it requires a closer look and a procedure as outlined in ASME PTC 4-2000 will take the variables into account, going beyond just the stack loss. Things like steam and feed water flow, moisture in the stack gas, so it would be moisture losses, and clocking of the fuel meter for actual input will provide the true indication. These factors will provide the true indication of how much of the fuel burn is actually going into the boiler water to make steam. Continuing on now with the methodology used for assessments, we're now looking specifically at the burner. And I thought it would be good to briefly review combustion and its effects beyond releasing heat energy. Now, referring to the chart on the screen, you see during the combustion process what the burner and its integrated parts are attempting to control. The red arrows are pointing to 100% combustion efficiency. This is where we are burning the fuel. There's zero excess air, zero hydrocarbon, zero CO, carbon monoxide. Only CO2, carbon dioxide, and water vapor remains. This is also referred to, as you've heard, as stoichiometric or perfect combustion, 100% efficiency as far as combustion is concerned. And then as we go to the left of the vertical, we go rich in our mix and we start to form carbon monoxide. And to the right of the vertical, we go lean or high in excess air. Now, going to the left is dangerous and wasteful. Going to the right is wasteful. So we want to have efficient combustion, but be on the safe side too. So the burner is normally set up at about 3% O2 or 15% excess air. They're interchangeable values. This becomes our benchmark and where we try to keep the burner operating most of the time, because as you can see in this slide, for every 2% increase in oxygen or O2 over the benchmark, we lose 1% in efficiency. And that is why, for simple math and visual effect, the arrows point from 3% to 7%, or a difference of 4%, meaning we would lose 2% in efficiency if that was taking place, varying from 3% to 7%. Now, the other thing to observe at this juncture in the process is how well is the boiler, which is the heat exchanger, absorbing the heat from the burner. Now, if the burner is operating and combusting properly, and all the surfaces in the boiler are clean, the temperature of the flue gas should be approximately 50 to 100 degrees above the saturated temperature in the boiler. In other words, if the boiler is operating, let's say, at 100 pounds, with a saturation temperature of approximately 340 degrees. 100 pounds is 338. Let's just call it 340 degrees. The stack temperature should range between 390 and 440 degrees Fahrenheit at high fire, 390 at low fire. Because the thing we want to note here, for every 40-degree increase over these base points, you lose 1% in efficiency. Note the arrows on the slide. The other thing the professional assessor is looking for are the possible climatic variables. Things like relative humidity in the boiler room or barometric pressure fluctuations. And then the most important, what about variances in ambient air temperature? For instance, on the screen, you see with the green arrow how the burner was set up with an 80-degree Fahrenheit temperature in the boiler room. That's how it was set up. Now note the bottom red arrow. The ambient climbed to 100 degrees. Does that happen often? Doggone right it does. But our excess air went from 15% to 9.6% because of the air density change. We're heading to a richer combustion mix and an unsafe sooting condition. Conversely, if the temperature drops to 60 degrees, which is possible, open up doors, windows, and so on, we're becoming lean with too much excess air and wasting fuel. So the professional will be noting conditions like this, because this could be a candidate for an O2 trim system, especially if the ambient temperature changes frequently and the boiler modulates a lot, because that's what an O2 trim system does. It compensates and adjusts for the variables, keeping the fuel-air ratio as consistent as possible. Now, I hasten to add here, it's not going to tune your burner for you. You need a technician for that. But it will compensate for uncontrollable fluctuations due to climatic fluctuations or differences. Now, at the same time, the professional is taking note of climatic conditions. He or she is also paying close attention to the burner's combustion control system. If it's a single point or a parallel positioning system with independent actuators for fuel and air, this is the best control system as it mitigates hysteresis, slip, and wear, which is common with a single point system. But if the boiler doesn't modulate much and the linkages seem tight and in good condition, they'll note that too. And then we need to pay close attention to the turn-down capability of the burner, as I noted earlier. How's it tracking the load? Is it cycling unduly? This is very expensive if it does because of the frequent pre- and post-purge losses. We're blowing ambient air through a hot vessel, purging those BTUs to atmosphere. This, too, would be properly noted. Finishing the major burner observations, we move on to other areas and external devices which can save energy. A big one, as I showed you in the beginning, is the stack loss. Now, if the boiler, let's say, is over 150 horsepower and it's operating over 100 pounds pressure, it may be a candidate for a stack economizer for recouping some of the stack loss energy by putting it into the boiler's feed water, which is coming from the feed water tank, which in most cases will be a deaerator, but it could be an open vented receiver. Remember now, for every 40-degree drop in that stack temperature, as I showed you earlier, we gain 1%. So the assessor will so note not only that, but also the appropriateness and the operating conditions for a possible application. But also, besides that, what's the physical conditions in the boiler room? And if an economizer can even fit when considering things like ceiling height, the overhead piping, and so on. So the juice might not be worth the squeeze, but certainly it shouldn't be overlooked with the assessment. Or what about the way the boiler is set up to control the totally dissolved solids in the boiler water, which, of course, what we're trying to do here is maintain the proper conductivity. What's happening to the effluent? Is it going down the drain, wasting these valuable BTUs? Might be a candidate for a blow-down heat recovery system. Again, putting those BTUs into the boiler's feed water stream before they exit to drain. You know, you'd be surprised at how much payback is possible depending on the boiler size and the percent of blowdown leaving the boiler. Again, something which has to be looked at and evaluated. Not necessarily going to be applied, but it's got to be looked at. Then, of course, the support accessories have to be checked, and at the same time, the amount of condensate coming back from the system. If little is returning and there's a lot of raw makeup coming in, is a carbon filter required if one is not already in place? Is the softener a twin or a single unit? And is it adequately sized? Is it charged and working properly to reduce the amount of calcium and magnesium which is entering the boiler? And you know, what about the chemical treatment analysis? Are there high degrees of carbonate and bicarbonate alkalinity? The assessor would have to ask, you know, would a dealkalizer be a good add to reduce the blowdown and then further protect the system? And what about the boiler feed? Is it a vented receiver or a deaerator? What's the operating temperature? Can it be elevated? How are the boilers fed? With on-off pumps? Modulating feed with constant running pumps? Well, what about a variable frequency drive on these pumps? The ones that are constant speed? How about the chemical feed system? And where are the chemicals going? Into the feed tank, or are they going into the boiler? These are all very important observations which need to be taken into account, and then they have to be documented in an assessment. Now, I said at the outset that we were going to be focusing primarily on the boiler, and the boiler room today. But to do that effectively, you still need to go out into the plant to see where the steam is being used and get at least some indication how effectively it's being employed. For instance, while going out to the plant, check the piping. to see if it's properly insulated, because if it isn't, valuable BTUs are being wasted to the process, and the chance of damaging water hammer is accelerated. And at the same time, the professional assessor will be looking for at least those steam traps which are readily visible and observing the types employed, because as you can see with this slide, they vary in design and in functioning. And as such, specific types are employed depending on given applications. Some just work better than others given these specific conditions. The other thing about traps, which is important here, is that no matter what type is employed, they have three specific functions. They trap steam, they evacuate condensate, and they purge air. Now, as far as air elimination is concerned, the trap helps, but it doesn't do the complete job. Air vents also need to be placed in strategic locations to eliminate air, or we will incur what is referred to as partial pressure conditions. Now this means, as you can see in the slide, let's say I have a steam line heating a process load at 86 pounds per square inch gauge. The temperature of that steam at 86 pounds is 328 degrees. You'll find that on a steam table. Now, if, however, I have air in with that steam equaling 10% of the volume, my temperature drops to 321 degrees, or the equivalent of 76 pounds, even though I'm registering 86 pounds on my steam gauge. What does this do? Well, it extends the process time, and it wastes energy. What the expert is also looking for is how are the traps piped. As an example, say we're looking at the steam header piping. Where are the traps? Are they at least every 300 feet? What about before expansion joints and before control valves? Do I have traps? What about the drip pocket? Is it properly sized with the proper drain valve? These are things we're looking for. So these are all good observations which need to be noted during the cursory tour, but what's really important at this juncture is how is this condensate being returned to the boiler room? Is it by gravity or sheer motive force, difference in pressure, or by mechanical means, such as the condensate tanks shown here? And, equally important, are there times when the condensate overloads the existing system and needs to be drained? This is liquid gold. And if this is the case, maybe a surge tank in the boiler room working in conjunction with the existing feed tank may be in order. Unbelievable the amount of waste we have seen over the years, which is not only BTUs, but water and chemicals as well. And then, what about venting at the process? Do I have a condition wherein condensate will back up into the process load or into the process if I don't vent it off? Am I venting flash steam through the roof using a flash tank and then dumping the condensate? As you can see on the slide, the flash alone can total anywhere from 7 to 15% of my total condensate energy just heating the ducts. Why not recapture this energy, if it is continuous, and pipe it to my deaerator for removing oxygen and carbon dioxide, and at the same time recoup some of the hot condensate BTUs from that flash which didn't flash, or that condensate which didn't flash, and putting them into the makeup water stream before dumping this condensate into the low pressure return line. Sounds practical, doesn't it? Unfortunately, this idea is seldom employed unless attention is drawn to it and the cost is justified. So that's the efficiency cornerstone that we'll be looking at today. But what about the second one, sustainability? And as you can see, this impacts the finite resources of fuel, of air, and of water, which, as we all know, is the sustenance of life. water is, and the awareness of its finiteness is growing every day. Thus its importance in a sound boiler room assessment. This water will be the next oil embargo psyche, which embroiled the world back in the early 1970s and still impacts our lives today, despite our recent fuel exploits. Fresh water is becoming a scarcity, and we have to become even more aware and involved with its preservation. And that's why returning condensate goes well beyond the dollars and cents. It's also preserving and sustaining a most precious resource for us, for humanity. And speaking about a precious resource, what about the air we breathe? We've all heard about the Clean Air Act, which evolved in the late 1960s and has been revised several times with major focus on NOx and CO. Well, I've mentioned in other webinars in the past that the industry has responded with an array of high-efficiency, low-emitting burners for reducing NOx and CO just dramatically. So for those facilities who are not in compliance, or those companies who are just want to be a good neighbor, there are options available which the assessor can advise on. And in some cases, such as California, for instance, the limits in NOx production, which is a precursor to ground-level smog, are very stringent, maybe less than 4 parts per million. And a standard burner without any NOx reduction is going to generate about 120 parts per million. So they're saying less than 4. And in these cases, the industry has again responded with a combination of flue gas recirculation and then employing a post-combustion reagent such as ammonia for further reducing the NOx to almost zero. And this is referred to as either non-selective or selective catalytic reduction. That's selective catalytic reduction I have a picture of now on the screen. Now, the other opportunity may be if the client has another source of fuel which is being wasted or flared off or just hauled away. An example would be a landfill gas or digester gas. We have technologies which can be used to burn many of these waste fuels. Now, on the slide now is one of our boilers, which is burning both natural and digester gas. On the right side picture, you see the dual canister burner with a set of orifices for the natural gas. Those are the sputted ones. And another series of larger orifices, which are flush, and those are burning or are used to diffuse or propagate, or I should say, allow the digester gas to enter the combustion area. Now, in this case, the way it's working is the primary fuel is digester gas. And when the digester gas pressure drops because of a depleting supply, the auto control senses this and automatically shuts the digester gas system down safely and immediately brings the natural gas service online with a minimal to no interruption in service. Just another excellent way to conserve natural gas while burning a renewable and a sustainable fuel in its place. So there are some ideas to look for when considering sustainability. Now let's turn our attention to the third cornerstone, which is reliability. Here we're looking for obvious signs on the burner which tell the experienced eye if the equipment is in good shape and up to date with the combustion control system and also with the burner management system, which controls all the burner sequencing and monitors the burner's safeties. It's also known as the programmer. What is especially important is the age of the burner management system or programmer. And if it includes all the lockout information in a clear and readily understandable way, and if it has the capacity to log and store fault history. These are extremely important information pieces which greatly assist the operator in keeping the boiler online and quickly returning to service in times of an unexpected lockout. What you're looking at here is a microprocessor-based system with considerable information presented, but there are better systems out there today. Systems which are PLC-based, programmable logic control-based, and integrate not only the burner and its operation and faults, but all the accessory equipment too. All integrated together with excellent visuals and touch screen interface. These systems really keep the operators informed and able to anticipate as well as quickly remedy unexpected outages. This often is key to ongoing reliable service, provided there's an inventory of critical spare parts on hand should the outage occur and it requires a part to expediently bring that boiler back online. And the other very important factor in achieving a reliable boiler operation is an ongoing maintenance program which diligently inspects and records critical areas on the boiler, its operation and its controls, and when things are looking irregular or questionable, and when, at this particular point where remedial action can be quickly applied. So the assessor will be looking for these types of records, which should also include service records that indicate when tune-ups were performed, including the efficiency checks. Now, from a reliability perspective, the assessor will be looking for elevated stack temperatures, which could possibly be caused by either fireside or waterside fouling, which along with energy loss could bring the boiler down too. Remember, we're looking at reliability now. And speaking of records, the professional assessment person will be looking for an office or a dedicated space to house records such as you see here, beginning with what is referred to as the critical records, things like the manufacturer's data report, equipment documentation, the serial number of the boiler, the national board stampings, list of suppliers with the contact information, spares, and so on. Everything that you see on the screen there. And then another set, which are often referred to as the dynamic records, which include things that you see on the screen now as well. The startup reports, the repair reports, all that kind of information that we need to be tuned into to keep this boiler reliably performing. And the boiler room log is critical and must be maintained correctly and religiously, or reliability and possible safety problems will definitely ensue. So the expert will be especially concerned with those items that I have in red, as they all impact reliability. Water, water visible in the gauge glass, that top one, very, very important. Is the gauge glass cloudy or scaled up? I want to be able to see that level readily. Steam pressure, how does it fluctuate? Feed water temperature, the flue gas temperature, these all relate to efficiency. These are critical items, the ones that I have in red. And when we're talking about improving reliability of the boiler, what I've talked about so far, including uptime, up-to-date programmers, burner management systems, good maintenance practices, and consistent record keeping, it really doesn't add up to a hill of beans if the people responsible for the boiler don't have a clue about what's going on and why they're doing what they're asked to do. This is where training comes in, be it general classroom training, tailored on-site programs involving your own equipment, or any number of web-based programs. There is a plethora of training programs out there, and there is really no excuse why operators and facility people should remain unaware of what they are caring for, how it works, how it's maintained, and equally important, the cost it imposes on the facility, to say nothing about the dangers that lurk within it if something goes terribly wrong. I'll say no more, as this is a good segue to talk about the last cornerstone for the assessment professional, and that's safety. And with the time that I have remaining, I'm only going to mention a few areas the assessor is going to be looking at. And this should give you a good grasp of the types of things that may need correcting. For instance, I showed you earlier how we would like to see drip pockets sized, where the trap should be located, and of course, the pocket should have a drain valve at its bottom for air removal when a system is starting up or restored starting after a cool down. And also it's there to rid the pocket from sediment and debris which could ultimately foul up the trap. Now, what we have encountered sometimes with some audits or assessments is the valve used for draining or purging is often a quick opening one-quarter turn ball valve with a handle similar to what's shown here. Now remember, this pocket is directly tied into the steam header, which is under high pressure. Let's say it's 100 pounds. That's 340 degrees. And if someone inadvertently catches a piece of clothing or bumps the handle on the valve, it could open sufficiently to seriously scald the individual and cause serious harm to he or she. So if this might be the case in a facility or one that you know of, the recommendation by the expert will be to replace this valve with a slow opening gate valve to greatly mitigate the chance of this possible scalding situation to occur. Now, another very key safety area which will be scrutinized is the condition of the low water cutoffs, both the main and the auxiliary. Is there any evidence of poor maintenance? And what does the boiler room log show with regard to the regularity of these devices being blown down, the connecting lines being inspected, and when, if ever, an evaporation test was conducted? Now, those of you who attended the webinar last month on checking safeties heard in some detail how this explosive event occurred. And yes, it was a malfunctioning low water cutoff which caused this boiler to launch through the building, leaving nothing but devastation in its wake. The low water cutoffs are a key safety check point. And the last safety check I'll mention today is the piping for the boiler's safety relief valve. Remember, if the high pressure limit control fails for some reason and the boiler continues to rise in pressure, the only thing left to prevent an occurrence is the safety relief valve. And they need to be piped in a certain way to prevent severe problems in the boiler room should they relieve unexpectedly. Looking at the diagram on the screen now, you see what the assessor is going to be looking for. You see the support of the riser pipe, which is larger than the discharge pipe. That goes up and it's free moving and secured at the ceiling or at the roof. Is the discharge pipe properly sized? Do we have a drip pan L? Do we have drain lines on it? This is the way these safety relief valves have to be piped. Now, there you have, in essence, what a thorough boiler room assessment evaluation will address, at least one which is centered on the 4 cornerstones of efficiency, sustainability, and safety. So after completing the observations, the next step is to sit down with the interested and responsible parties and review the findings. And that normally starts with the major discoveries. Now, some typical ones would include uninsulated piping or major pieces of boiler support equipment, which, if insulated, could save energy. For instance, a 6-inch steam pipe at 100 pounds, 338, 340 degrees, radiates approximately 1,650 BTUs per hour per foot. Now, figure 500 lineal feet of uninsulated pipe, that equals 826,000 BTUs per hour. That's 25 horsepower. Production hours are 4,000 hours per year, conservatively. At 65 cents per therm for natural gas, that's $21,476 wasted. Annual fuel bill is over $500,000. That's 5%. Another typical discovery is steam leaks. Look at this. We've got a steam leak that equals 1,000 pounds. 100. We've got steam leaks that because we got an opening in the piping that equates to a half an inch. We're operating that boiler at 100 pounds, that steam line at 100 pounds. At a cost of $7.50 per 1,000 pounds, we're losing $55,451 a year. Some people walk through these plants and they see the steam or the condensate coming out of these pipes. They say, been there all the time, don't worry about it. Well, it's a huge cost of doing business that could be recouped if we stop those leaks. Here's another typical discovery which certainly impacts safety. Safety valves whose discharge is going into an undersized riser vent pipe, which is hard piped through the roof. Now, making matters worse, they've manifolded them together, which further exacerbates the back pressure problem should the valves discharge. How this got by an inspector, I'll never know, nor should it have, as this could easily cause the valve and or the piping to contort and fail, spewing all that hot steam and condensate through the boiler room. Very dangerous. Remember what I just showed you. Those safety valves should be piped independently with adequately sized vent riser piping, which is free-floating and properly secured and supported at the roof. Anything less, and we're asking for trouble. Now, here's another common discovery. It's a phenomenon that we refer to as stall. In this situation, they are incurring intermittent product heating problems caused by the trap on the downstream side of the heat exchanger losing its differential, allowing condensate to back up into the heating unit and thereby lose its heat transfer capability. So that's a separate shell and tube heat exchanger that I'm showing you here. But it can also happen in a jacketed steam kettle, as you see in this particular case. But in any case, the result is the same. Lost energy, lost production, and most probably lost product. Then, following this cursory discussion at the completion of the assessment, the specialist will return to the office and prepare a formal report for all that was witnessed, including the discoveries, and then a path forward for that particular client. It will contain information such as you see here, and which was taken from one of our clients, but I'm sure other reputable assessors will prepare something similar. So you start with the executive summary, kind of an overview, get into detail about the boilers, how they're performing, feed water system, the safety relief valves, and then a roadmap or a path forward for attacking those cornerstones. And sometimes these reports will contain markups of the plant's existing P&ID drawings, which is the process and instrumentation diagram. Some plants have these. So that will be a tool which then could be detailed, showing the highly recommended changes for improving one or more of the cornerstones that we're looking at. Now in this case, it's a pump manifolding that was suggested, and also suggesting a modulating feed water introduction. There was also, in this particular case, there was also an excellent opportunity to save considerable energy through the use of a dual economizer, wherein there were two sections. One non-condensing section for further heating deaerated feed water, and because they had a need for cold water heating, a condensing section was put on top for this purpose. So the condensing section is now grabbing the latent energy from the exhaust gas after it's gone through the non-condensing section, lowering the stack temperature to below the dew point, adding significantly to the fuel savings. That is what a boiler room assessment is all about. It's an excellent opportunity for a company to deeply evaluate its steam plant operation, and by focusing on the four cornerstones, efficiency, sustainability, and reliability and safety, the customer can rest easy knowing the operation is not only operating efficiently and reliably, but safely and in a sustainable fashion as well. So here are your takeaways today. Good assessments follow a logical methodology involving the 4 cornerstones. When evaluating the cost of steam, make sure you're looking at loaded cost, not the unloaded. Make sure you've got all the costs included in the cost of steam. There are various efficiencies. When evaluating the boiler efficiency, it should be the fuel to steam efficiency that you use. The O2 trim system compensates for uncontrollable atmospheric changes such as ambient temperature and barometric pressure. It won't tune your burner. After it's been properly tuned, it will compensate. Air in the steam system can significantly reduce the temperature, reducing heat transfer, increasing fuel cost, possibly affecting the product. Steam leaks add up, as I showed you, and greatly impact the cost of operation. Properly functioning low water cutoffs and properly piped safety valves are key safety checkpoints that the assessor will be evaluating. A good and reputable energy assessor can greatly impact a company's bottom line. So with that, we can have some questions. Hopefully they've been texted in, and Susan will read them to us.
Thanks, Steve. Yes, you may text in your questions, type in your questions using the Q&A tool on the WebEx control panel, and if you will put that to all panelists, we can all see those as they come in, and I'll ask the questions out. So while we're waiting for questions to come in, Steve, I'm going to take the control back because I'm going to let part of our expert panel explain a tool that we have available today for download so that participants can download this and use that for additional information. Give me just a moment to take back the reins. Let's see. Here we go. And our expert panel is Cesar Lavano and Randy Smith. They are part of our boiler plant optimization team. They're in and out of the boiler room all the time, assessing different areas for efficiency and energy savings and financial savings as well. Cesar, are you going to be the one to go over this tool, or do you want Randy to do that?
No, I can go over the tool.
Okay,
Are we talking about the boiler plant optimization scorecard?
Yep, and it is showing on the screen now. And while we're waiting for the Q&As to come in, I'll let Cesar explain this tool, which will be located on the Cleaver Brooks website for your use. And also the slides will be available. They should already be up there on the Cleaver Brooks website, cleaverbrooks.com/webinars. And if you'll give us just a little bit after the close of this session, when the recording is finalized, we'll have that recording posted as well. So again, if you requested a certificate of attendance, you'll get that by Friday afternoon, hopefully, and you can use that to submit for your professional development hours. And if you did not request one on the registration process, you may email us at webinars@cleaverbrooks.com, and we'll be sure that you get one. All right, so Cesar, I'm going to let you explain the tool that will be available for them on the website as well.
Okay, great. Thank you. Thank you, Susan. Yes, the boiler plant optimization scorecard is just basically, just keep in mind first before I go into it, is that all plants, all facilities are different. So some of these things may not apply. So when we're looking at a facility, the idea behind the scorecard is for someone to go and look at what's in the scorecard, these items in there that have been broken down into various categories. One category is documenting the current state of the boiler. The other one is operation and maintenance, prepare for operational recovery, and then opportunities for improvement and the educational training. And that's for a facility to self-evaluate how they look at their facility in these areas, which really shadows what we've been talking about with the boiler plant optimization and the topics that Steve Connor shared with us just a moment ago. So what it does is give an overview for a facility of the areas that they should be looking at to kind of self-evaluate themselves to see how they can make improvements in areas that probably weren't looked upon before, and gives them just a general kind of benchmarking philosophy of going into these various areas that we just broke down into tasks. And that's, going into these different columns, someone can just add up what they have and what they don't have, and obviously what does not apply, and give themselves a self-evaluation and look upon themselves to say, well, do they need to improve, or look at these other areas that probably weren't not considered. So again, this is just more of a self-check tool that can be used, and if there's areas there that you identify as a deficiency, we'll give you the ability to identify that and then see what is the path forward to try to overcome a deficiency or something that's missing within the facility.
All right, thanks, Cesar. And you can get this scorecard. It is already located on the Cleaver Books website. If you go to cleaverbooks.com/webinars and look under today's presentation topic, all the materials for today's presentation topic will be there. Just give us a few more minutes after the close of the session to get the audio and the recording, the video up there posted. All right, time for questions. We do have a number of questions that